Welcome back to BAS 121. Today we're going to go through example 9.10 in the book. So up until now we've been doing regression on a single independent variable. We've been trying to explain our dependent variable based on one independent variable. So for example, graduation rates based on the average SAT score, or time it takes to mow the lawn based on the length of the grass. What we're going to do now is we're going to take a look at multiple regression. What if we wanted to predict graduation rates, which happens to be this example, based on several variables, such as average SAT scores, such as what was the student's class rank in high school, versus what was the college's acceptance rate. Were they very selective in the students they picked, or were they not very selective in the students they picked? How expensive was the college, with the theory maybe that a very expensive college is going to have higher graduation rates? But the whole point is, how do we take multiple variables? And the reason we want to do that is we might get a much better model. If you think about it, we're probably going to get a better model that explains more of our variation if we do multiple regressions. So the example we have here is we have raw data on several, I find it kind of interesting, several colleges and their graduation rates. And I'll show you down here the raw data. So you have it in your colleges and university file. But here are the different schools. Here's the median SAT scores to get in there. The acceptance rates of the college. So this would mean Amherst only accepts 22% of its applicants, as opposed to Grinnell that accepts 67% of its applications. Here's the expenditures. So I guess you don't want to tell your sons or daughters about Caltech. The cost of the college. What percentage of the students that were in the top 10% of their high school class? And we're going to use these four variables to try to predict the graduation percentage. Now the way you do that in Excel is you just simply go to data analysis, and you say, give me a regression analysis. And then, just like we did with the other, you say, here's my y variable, or my dependent variable was my graduation rate, what I'm trying to predict. And then over here, what's my input area? And that is going to be these four factors right here. Nice thing about Excel, I can do all four at the same time. I've included the labels in my highlights, 95% confidence interval. This won't be, I'll just do this for the video, just so you see we get the same thing. Range, output range, yeah, we can put it there. You can do a new thing, put it there, say OK, and you get all this raw data, which looks a little bit daunting. So let's break this raw data down, which I've done for you up here. And in the green, you don't get this out of Excel. These are the explanations I've added. And I've also added some yellow highlights to kind of say some of this stuff's a little more important than some of the rest of it. It's all interesting, but some of it's more important than others. So the summary output, first of all, you get what's called a multiple R, which is basically the square root of R squared, or sometimes just often called R, or the correlation coefficient. If you've forgotten what a correlation coefficient is, it's all down here. It's basically, it gives us a value between -1 and 1. And the key things to remember is a negative number is a negative correlation. A negative correlation is where as one variable goes up, the other goes down. So in this example, we might think we're going to get a negative correlation between acceptance rate in graduation rate, because as I accept all my applicants, I might expect my graduation rate's going to go down, i.e., a college that has open admissions and accepts 100% of all students is perhaps going to have a lower graduation rate than a college that is very selective and only takes 10% of the applications. A positive correlation might be something like the SAT scores. The higher the SAT score, perhaps the higher the graduation rate. But we're not going to be guessing here because we've got the data and we'll see what it says. But that's just a reminder of what a positive correlation versus a negative correlation is. And then if you've forgotten, so that's and then the R squared, just as squares are R. And so that makes it somewhere between 0 and 1 for R squared. And if we remember from our beginning of regression, the closer to 1, the better the correlation. The more the correlation determination says, what percentage of our variation does our model explain? Well, the more and more and more of the variation that's explained by our model, the better the model is. Now, we'd like it to be 1. In the real world, if we get something above 0.8, that's pretty doggone good. So that's just a reminder of our R and our R squared. R is our correlation coefficient. R squared is our coefficient of determination. Now, if we were having doing this on a single variable, we'd say 53%. Our model explains 53% of the variation, which isn't great, but it's of use, right? Because it's explaining over half of the variation. Our adjusted R squared is used for multiple regression. This is basically saying 49, or roughly half of the variation, is explained by our 4 variables, which again is not perfect. We'd like it to be up in 80%, 90% range, but it is of value because it's explaining quite a bit of it, and we're going to see in a minute it is significant. The standard error is just simply an estimate of what our standard deviation is. And the number of observations just tells us how many observations were in our regression analysis. So that's the summary output. The 2 key things are, if you're doing a regression on one variable, you want to look at the R squared. Multiple regression, you want to look at the adjusted R squared. Now, the analysis of variance section gives us our regression, our residuals, and our totals. And over here it gives us degrees of freedom, sum of squares, mean squares, our F statistics, and the significance of our F. So let's remember what analysis of variance does. Analysis of variance takes all our variation and splits it between its components of whether it's driven by our regression equation, or sometimes called explained variance, or whether it's our residual portion or our unexplained. So that sounds a little complicated to me. So maybe you get it, but for me, I want a simple example. So hopefully this will help. I did a very simple example of said, let's pretend that class attendance is a pretty good predictor of test scores on the exam. So students that attend class tend to do better on the tests than students that don't attend class. So I made up some data, and of course I made it up to kind of prove my hypothesis, but that's neither here nor there. And I took an average of 80. And I simply did a scatter plot, just a reminder of how to do that. You did highlight my area, insert scatter plot, and do a scatter plot. And I can click on one of these, add a trend line, a linear trend line, show me the equation and the R squared, and I get all of this. And all I added here is a red bar. I simply went up to insert shape, picked a shape, and drew my red bar. Now, and then I exploded it down here so you can see what's going on. What analysis of variance is going to do is the sum of squares is going to take every one of my data points and says, how far from the mean is that point? And square it. And the reason I'm squaring it again is otherwise my negatives and positives would offset each other. And I add them all up for every. So in our college example, for all 49 data points, Excel is going out to each one and saying, how far from the mean is that point? And squaring it and adding them all up. And that's our sum of squares. Now, what analysis of variance is going to do is going to say, well, okay, let's take this data point right here. How much of that is explained by our regression model? Well, what it's going to do is it's going to say, well, let's take the mean and let's go down to what we would have predicted with our regression model. And we're going to say that variation is explained by our model. Our model would have predicted that variation from the mean. We expected these people with very little class attendance to actually score very low on the test. So that deviation is explained or is by our regression model. Now, this is what we would have predicted in the regression model for someone with approximately a 60% class attendance. Now, they didn't score exactly on our regression line, so there's some residual difference. That's what's called the residual or the unexplained. So hopefully you can conceptually see what's going on here. If all our data points line right up with our regression model, what that's going to say is, all of the deviation or all of the variance is explained by our regression model versus which would make it a very good model. So going back to these data points, the more and more of this, we want to see a very high number here and a very low number here. This F statistic is simply, if you remember the mathematical equation, it's not complicated. It's just saying how much of our mean squared is explained by regression divided by how much of our mean squared is explained by the residual. That gives us our F stat. Again, the higher that number, the better our model is. What this is this just puts it in terms of probability. The probability that we are not explaining at least a portion of the deviation with our model is almost zero. So that's very good. What that's saying is our model explains part of the deviation. It's significant. Okay, so just to review, the ANOVA, or the analysis of variance, splits the sum of squares between its components. Its components are how much of it is explained, i.e. the regression portion. Sometimes it's called between or within. Residual value is the unexplained portion. The degrees of freedom, the total is just our observations, or our n minus 1. The regression portion is just the number of independent variables. And the residual is just the difference between our total and our regression. The sum of squares we sort of went through is the sum of, we take each observation, compare it to the mean, square it, and then add them all up. So if you did that for every one of, that's what you would get. The mean just takes the average of our sum of squares. The F statistic, we said, is saying how much of this is explained by regression and how much of this is explained by the residual. And the way it does that is it says, I'm going to take my mean squares of my regression and divide it by my mean squared of my residuals. And my significant F says, what is the probability that the variables do not explain some of the variation of the dependent variable? So the probability of that it does not explain, that graduation rates are not at least partially explained by those four variables, is almost zero, which basically allows us to go back to hypothesis testing. If our null hypothesis was these variables have no significance and no explanation of our dependent variable, this will allow us to reject that null hypothesis and basically say, yes, these variables do influence graduation rates. Now, the next section gives us our coefficients, so it allows us to write an equation. So the equation is graduation rate is equal to our intercept, 17.92, plus, because this is a positive, 0.072 times our medium SAT, minus 0.285 times the acceptance rate, minus, hopefully you get the gist of this. And this gives us our p-values, which again, we want to be relatively low. Now, some key points. What this is saying is our graduation rate is positively influenced by mean SAT scores, because this is a positive number. So that makes sense. The higher the SAT score, most likely the higher the probability that the person is going to graduate. The acceptance rate. Now, this is a negative number, so we have a negative correlation. But that makes sense to me. The higher my acceptance, the more, if I have open admissions and accept everybody, then intuitively I would say it's going to be more challenging to graduate all those students. If my acceptance rate is very low, i.e. the college is very selective of who they allow into the college, then chances are my graduation rate is going to be higher. Now, these next two are kind of interesting. The expenditures is actually a negative correlation. The more money I spend, the graduation rate. Now, you notice that it's almost very little correlation because the number is so small. It hardly influences the graduation rate. But it's interesting that it's a negative correlation. So we've got to think in terms of what might be going on here. What might be going on, I go to a very expensive college and I say, I don't want to spend all this money. I start at Caltech at $120,000 or $102,000 a year, and I kind of say I really don't want to go through this. That's a hypothesis of what might be going on. We'd have to research it further. This is an interesting one too. The class rank, at least on our raw data, doesn't have a high correlation to graduation rate. We'd have to look at, maybe it's a lot of the Bill Gateses of the world that are so intelligent they don't finish college. Not sure what's going on there, but this section allows us to come up with our equation. Now that we've come up with our equation, we can put points in there. And that's the example on how we do multiple regression. The only other thing you've got to keep in mind with any regression is the model should only be used for variables of the independent variable within the range. So what that's talking about is you can get some funky things going on, right? If you think of height of children, I might get a linear regression if my data is only from ages 0 to 5, but certainly I can't extrapolate that on out. People don't keep growing forever. So, that's just saying that most regression analysis is only useful within a range. That's example 910. Any questions? Let me know.